So welcome all, and today at the Code Seminar we will have Blažej, who will be talking about parameterized complexity of Eulerian strong component arc deletion.
Thank you. Yeah, this problem name is very long. I will shorten it to SCAT, but the point here, at least the first target I want to do, is to explain what's the problem about. So, say you are given some input graph like this. All of the edges are the same, right? The colors are just explaining the meaning. And you are searching for a edge cut. So those are the blue edges here, such that if you remove those edges, in the resulting graph, every strongly connected component is Eulerian. So let us see what it means. So if you remove the blue edges here, you notice there are 3 strongly connected components. Those are the black edges. The green edges are coming between strongly connected components. If you never heard about strongly connected components, it means you can always reach from one vertex to the other and back, right? So there are like cycles, but it may be more complicated than cycles. And so at first, removing the blue edges breaks up the graph into several strong components. And if you remove the green ones, which are coming between them, then you end up with several connected components, each of which should be balanced. So balanced means here that the number of edges that are coming to a vertex is the same as the number of edges that are coming out of the vertex. And a graph that is balanced and connected is called Eulerian. So this is why there is this name of the problem. Right. Formally, this problem comes from a related problem, which is more known than it, which is feedback arc set. This is a variant of feedback edge set from undirected graphs. And the target in feedback arc set is to remove some set of edges so that you will have no cycles remaining in the graph at all. Right, so once you remove the blue edges here, there is an order of vertices from left to right such that all edges are coming to the right. The difference here, basically, if you want to compare these two problems, you could also pose this as a variant where every strongly connected component is of size 1, right? Because there are no cycles. So every strongly connected component is trivial. If you allow them to be bigger and you require them to be balanced, that's the problem that we are targeting to solve. Okay, by the way, if you have any questions during the talk, please interrupt. You can notice immediately that in the solution, you will remove a set of edges, but there will be essentially 2 different types of edges. One type of edges in the solution basically breaks up strongly connected components. And the second type of edges, which is G and H here, will make the components balanced. Right? So, because those are the 2 targets of problem. Consider a variant of the problem where you would use only this type of edges, which make it balanced. So if your target wouldn't be to make only the result balanced in each strongly connected component, but to actually make an Eulerian graph, which would mean, okay, I want to remove edges so that the result is connected and balanced. That's like a different variant, right? Because you have no green edges like that. So that would be deletion to Eulerian graphs. But in our case, yeah, the big difference are these green edges. In the past, that was the variant that was also studied. So if you want it balanced and connected, then there are these 2 papers that studied it before. There was FPT algorithm for it, and then it was improved to single exponential algorithm. And if you focus on removing vertices instead of removing edges, then this was studied also like 3 years ago. And this paper that removes vertices and this paper both ask the question, okay, what if you remove edges? Which is the problem that we study here. Let's start with NP hardness, right? Why would we do parameterized complexity if it were NP hard? The related problem that I showed at the beginning, feedback arc set, is NP hard, is one of the first problems shown to be NP hard by, who was it? Karp? I was considering this. Both start with K, right? Yeah. And the reduction goes as follows. So you are reducing from vertex cover, which then was called node cover, and you will take your graph, you split every vertex into two copies, and for every edge that connects to vertices, you create like a pair of edges. So from the lower vertex, you draw edge to the upper vertex, and then lower vertex here, you connect to the upper vertex of the other one. You make this like cross edges. This creates a 4 cycle for every edge here. And the point here is that our problem, the feedback arc set, you need to cut every cycle, which also includes these 4 cycles. And if I decide to cut this edge, then I could just move this solution to cut this C edge. Right? And if you move all of these, what you have that for every 4 cycle, you must have chosen this one or this one, which models the original problem where for every edge, we must have chosen one of the incident vertices. So this is like vertex cover 2 feedback arc set. For our problem, we use very much the same thing. You just double the edges that are coming between the respective vertices. So what happens here? Right? In our problem, you want the resulting strongly connected components to be balanced. The problem that it creates is that you could have left this 4 cycle untouched. It could have been balanced in the result. Right? So it is not clear that you would pick this edge or this edge to model vertex cover. But if you double it, the thing is, now this vertex is not balanced because there are too many edges coming in. And if you kept this 4 cycle, then there would be simply too many edges that are coming here. And even if you kept it balanced, you would have picked one of the incoming edges, which you can just move to that vertex and cut everything. So this results in proof of NP hardness. And because vertex cover is NP hard for maximum degree 3, you get that through this reduction, you have bounded degrees in the resulting graph, and still Eulerian strong component arc deletion is NP hard with bounded degrees. So we apply parameterized complexity. Because we have the NP hard problem, let's see where it is tractable and why not. So I will try to give you a rough understanding of all of these results, which make up the paper. What we just saw is that on the very left bottom, that the maximum degree is NP hard, even for the fixed parameter of maximum degree. And we will see that it is XP with respect to treewidth alone and solution size alone. It is W1 hard for vertex cover and solution size. And we'll see FPT for treewidth plus solution size and treewidth plus maximum degree. Those are very similar, and I will touch on them at the end. Okay, so let's build some gadgets. Okay. First, first thing to do and to notice, we will allow multi-edges for now. And this will be the variant of the problem where you allow multi-edges. Say you are allowed to kill or to cut k edges, so you can remove at most 4. So if you have two vertices that are simply connected with more than 4 edges, then you cannot cut all of them. So they must. So at least one of these edges still exists at the end, right? If you do the same thing back, then you ensure that these two vertices are in the same strongly connected component in the end, in the solution. And moreover, they are balanced with respect to these edges, right? The same number of edges are going forward, same number as back. There can be something else, but with respect to these, it is balanced. So this makes these two vertices inseparable. And a different observation, if you make a path that's longer than k, so bigger than 4 in this case, and you make a few edges like that, the point here is that you can cut the path, making each of these guys its own component, but you can't make it slimmer, right? Because if you wanted to cut one edge from each of these paths, it's simply more than k, so you don't have the budget to cut one from each. So this will provide us with a binary choice to cut or not to cut. And this will be very useful in other gadgets as well. So let's combine these. So in a construction, let's say you want to have two vertices that are connected with fixed number of edges, and you want these edges to be undeletable. The problem originally doesn't really allow for this, but if you okay, undeletable. What I mean is that you want to make these undeletable. So what you can do is to make a path like this with this many edges, and for each pair add many edges that connect them forwards and backwards. What this gadget forced is that these two will end up in the same strongly connected component. If you do it for every pair, all of these guys will end up in the strongly connected component in the end. And if you made it long enough, then you can't cut an edge here and an edge here and that edge here, right? You can't make it slim. And if you try to cut it somewhere, well, you can't because it's too much, it's too connected. So there is no way to delete any kind of edges from here because you will just make it unbalanced in the result. So that's how you can model undeletable edges. The second construction, which is very, very similar, is that you want to make two vertices and you want there to be two choices. Either you will keep all the edges or you will cut all the edges to make a binary choice. So that one is simply this path. I described it before. You can't make it slim, but you can cut it. So that's exactly that. Just hide all these middle vertices, right? And they will model, that gadget models this. If you connect all pairs very much, you are modeling undeletable edges. Right, so to do an NP hardness reduction, we need some way to choose things in general. It's not very useful. And the choice gadget looks like this. So I will not draw them on the table anymore. Here you have 4 incoming undeletable edges, and you have 6 outgoing ones, made into pairs, which are in these gadgets, where you can choose to cut them or not to cut them. And because in the result, you will ensure that kind of the first 2 left vertices, because they are undeletable, they will end up in the same strongly connected component. And the middle vertex here would be unbalanced. So you need to preserve exactly 4 outgoing edges. And you are forced to cut either all the edges to A, all the edges to B, or all the edges to C. And this is a choice gadget. Now you can propagate that choice. So let's say you chose Y, and now in Y, this choice removed some incoming edges. And if it were balanced before, now it became unbalanced. So you must now choose some outgoing edges to cut again, so that it is balanced in the result. What this basically boils down to is that one group of these choices will be a color class. So I guess let me first remind you what we are reducing from here. Introduce the problem. So multi-colored click. You are given a graph G and integer K. And the partition of the vertices V1 up to Vk, partition of the graph's vertices. What this means, under the partition, you can imagine that the vertices are colored. There are K colors, so some vertices are blue, some vertices are red, and some vertices are square. And you have edges in the graph, of course, as before. And your task is to find a clique on K vertices such that it contains exactly 1 vertex from each color. So you would find these 3. You have a square, blue, and red, and they are all pairwise connected. So that's the multicolored clique. Oh, like that. And this problem is like the stable problem for parameterized complexity. It is known to be in some hardness class, W1 hardness class, when we parameterize by K, which is the size of the clique and the number of the colors. And I'm aiming to model this problem, to reduce it to our problem. So for one color class, let's say red, I will have 3 choices for the vertices. I will have a choice to select into the clique the vertex U, V, or W. And I do this for every color. Now, if you choose that vertex, we model it by cutting these edges, which propagates this choice further. And this propagation will result in cutting some further edges. Those are basically saying what edges will be in the clique. So if I selected this guy, V, from V, to be sure that it is in a clique, you need to cut an edge from V to square, from V to a blue vertex. Right? But there are several choices. You could decide that this edge is in the creek, this edge is in the creek, or something. So we want this one to select these two, this vertex to select the same, like the edges from the other side, right? And you essentially want these three choices to agree on the edges that are in the creek. So that's the big task now. Well, how do we do that? If you have the selection gadget for each color class, and imagine you selected these three vertices, then the choices you propagate further are modeling the edges, and those edges are modeled by a layer of vertices here. So a UV edge, UW edge, and BW edge. These edges have exactly two incoming, these vertices that model edges have exactly two incoming edges. And these are like the core why the deduction works, right? Because if you have two incoming and two outgoing edges, you can make it slimmer, making it one incoming, one outgoing, or you can cut it using two cuts, right? Which makes these other edges to go between strongly connected components. So they are basically inactive in counting the balances. So these two choices make the vertex inactive. This makes it slim, but you notice the budget you used is you cut two edges, as you did here. Or you could just keep it. And the whole thing boils down to, like, there is this master vertex, which is the sink and the source. So this is like a circular construction, where this vertex is the same as this vertex. And that one is like slightly imbalanced. And the only way you can make it balanced is to make these edges inactive. But to make them inactive, you need to cut these, and you need to cut these, and you have exactly the budget to cut like one copy of those edges in the first layer, one copy in the second, and that's it. And you need to make these in the third layer inactive as well. And that means you can choose only these two variants of how to cut those edges. Okay, that's it. What does it show anyway? W1 hardness by the solution size, right? Because before we had multicolored Greek parameterized by number of vertices in the Greek, and for each of these vertices we cut two edges here and two edges there. It's proportional to the size of the Greek. Okay, so we just showed this W1 hardness. Arguably the hardest one, kind of the non-trivial idea of these. Yeah, for a very long time it wasn't very clear how to use the fact that strong components break off from each other to model something. And the simple vertices that are these two incoming, two outgoing edges are basically the only one that break off from the main component, and this is sufficient to model the problem. Okay, so that's one reaction. Another one. So in this one, I think the main takeaway is that unary beam packing is W1 hard by the number of pins. What is this about? So you may have heard about beam packing. You have a set of items, and you have bins. Let's say you have B bins.
Could you please use different pen?
Oh,
Let's draw some more material.
you have H bins, and you want to put the items into bins. And basically, you can imagine the bins like this, and the items are like squares differently sized. Squares with different heights, or rectangles like this. And you want to assign them here in some way so that they don't overflow the capacity of the bins. Yeah. So H and B, where H are the bins, and each has capacity. If you take this problem and you limit the number of bins, then this problem is W1 hard, even if you encode the items in unary. Which is very useful if you have just a graph structure. You can model them by the number of edges. Unary encoding helps a lot. So we do exactly that. We will have a single gadget. I will show that later. And those represent bins. So you have these top vertices that represent bins, and you have many edges coming from the left to right. The point of these edges on the top is that they are just too big, and you can't let two bins to be in the same strongly connected component in the result. Because if you did, these edges across would make them imbalanced immediately. And there is no hope of saving them. So, okay, you have that. And then every item is represented by a single vertex. You connect them like by pairwise edges, and the number of these edges is the size of the item. And you connect them to all the bins. So you can notice that if you decided to not cut U from X and some other bin, then X and the other bin would be in the same strongly connected component in the result, which is impossible because of the top edges. So you must cut U from all but at most one bin. And you can do it like that. So we set the budget to be the number of bins minus 1 times some of the items. And that gives you budget to do these, to cut them like that. So for all the bins that are in the order before, you cut the incoming edges. For all the bins that are after, you cut the incoming edges to you. Which results in you being in the same strongly component as X. So this assigns each item to one of the components. Now, each bin is the familiar imbalance gadget. So we have two vertices that are well connected, and you have many edges that go just forward, and that models the capacity of the bin. If you let this vertex to be in the same component, it creates the cycle and it alleviates the budget, right? So it satisfies part of the budget. And if you let enough vertices to be in the same component, the component will become balanced. This may raise a small question, which I'll show you if someone asks. Okay. So that is W1 hardness by vertex cover. Because in this construction, if you remove the bin gadgets, which is just 2 times H, you end up with independent set. Cool. So, I'm not sure how deep. How much time do I have?
10 minutes.
10 minutes.
10 to 15 minutes.
Okay. I think we can make it. So yeah, this is just for I unfortunately today I will not explain treewidth. You know, ask me if you want, but let me just assume that. So you have the current bin that you are processing in some past, and what you kind of want is to have all the information about reachabilities among vertices in the bin. Because an edge that is in the bin is active, meaning it counts towards the balances, if and only if it is these endpoints are in the same strongly connected component. And it is inactive if they are in different components. The third choice is to cut it, right? So you have these three choices. And if you just model all the reachabilities in the bin, you have a reasonable state. But the problem is that you need to keep the imbalance of the vertex. Right? So if you, for example, if you had a bag and there are many components that come in and many of them have like incoming edges, and you would keep them all, perhaps some vertex here would incur huge imbalance because it has many incoming edges. But afterwards, it will like lose that imbalance because there are many outgoing edges as well later. So I want to keep the information of the number of incoming edges minus the number of outgoing edges. And I can forget the vertex only if it's imbalanced 0. So this immediately gives you like the maximum imbalance. What is it? Maximum imbalance to the treewidth. Wait, yeah, and maximum imbalance is essentially n at the very beginning. So this is xp. But you can notice if the vertex has a small degree, then this can't really happen too much, right? It can have some incoming edges, some outgoing edges, but it can't get too big because it's bounded by the number of neighbors. So this also gives you FPT. If you combine the parameterization, you have bounded maximum degree and bounded treewidth. The similar thing can be done if you bound it by the solution size. There is a small observation that you can do via maximum flow. So if you consider a solution, if you consider this like partial graph that you already processed with a fixed reachability like configuration over there, and you consider how the solution looks like, right? It cuts some edges possibly from U to V. But the number of edges you cut this way is at most k. So the maximum flow from U to V in the solution differs from the input by at most k. Which means that if you compute it during processing of the treewidth, you know that the solution is in a small window around the maximum flow. And you can, even if the imbalance is big, you know it can't be too different from whatever it is on the input. But the flow, the resulting flow can't be too different. So this allows you to keep a small state, meaning FPT mobility. So the first one was just treewidth, and with two combinations with solution size and maximum degree, you get these two FPTs. The open question, yeah, approximations, we didn't do any approximations, and possibly In the hierarchy, you have feedback arc set right around here. We tried a little, but there is no clear approach. 5 minutes? Okay. So let me switch completely to something different. Some of you may suspect. So you may be puzzled by this picture, right? There are some parameterizations, you have some like graph properties that are related to each other. What I want to show is that I've been working on this website where you have exactly this information. You have various parameters on graphs, you have their relations. So if that parameter is bounded, it means that this parameter is bounded. There's a relation here. There is little more complete information that you can get from it. So there is also like a complete pairwise table and some information about all these parameters and how important they are, roughly how important they are to the field, right? So if you go to the treewidth, you can see how it is related to other parameters, how it is related to graphs, graph classes, and some results that, like, these are some of the publications that lead, that have these results in them. And I will be very happy if you find it useful, or you find some mistakes, you let me know, or if you have some ideas on small projects that could be implemented there, because I think there is some area of improvement, possibly for some students here that could be led by lovely teachers here, right, as well, possibly some like final thesis things and stuff like that. Okay, that's about it. Thank you.
Questions? Maybe I missed it, but why does the feedback edge set in this case upper bound the treewidth plus the solution size?
I didn't tell it to you, so you didn't miss it. To think a little bit. So if you have bounded feedback edge set by k, right? And I can remove k edges to make it a tree or forest. This could be a solution, right? To our problem as well, because in a tree, every strongly connected component is balanced.
But it's the underlying undirected graph, right?
Yes. So feedback edge set is very strong in this sense.
It depends how exactly you define it.
Feedback edge set.
Or if you have two opposing edges, whether you have two edges in your graph or just one. So it's point to be.
So solution size. And then it's just wrong just by the solution size.
No. Like, I mean,
if I can delete feedback edge set number many, then the solution size will be bigger.
Alright. I mean, even if you have a forest, it can still be a strongly connected component and it can be in the last.
Depends how you define the underlying undirected graph. Okay, if you define it as for every edge which is directed, I will add an edge to the graph and I can have multi-edges. Okay. Then it is clear. Okay. In the other case, if you define it like, okay, for every edge, every die-edge, what do I do? I could squeeze it into single edges, but in that case, okay, in that case I don't think you can bound it easily. I believe this feedback edge set is just undirecting all the directed edges and keeping the multiplicities.
Maybe for the other case, your vertex cover lower bound. There are not too many edges, like in terms of between which vertices they go.
So if you kept the multiplicities, Oh wait,
No, if you don't.
if you don't keep them, then the feedback edge set is even bigger, right? Because you need to like cut these multi edges. So that's it is.
Yeah,
It is.
we can discuss this so far. I have a question. So now we're talking about the multi edges. So what happens if you don't allow them?
Yes, a baited question, arguably. Yes. So what happens here? If you don't allow multi-edges, what you can do is, in any construction, you can subdivide the edges once, and in that case, what results is a simple graph. So what happens to these reductions is that you lose this vertex cover, of course, because you will have deletion into stars. And for vertex integrity, there is a matching hardness. I believe it will, wait, no, tractability, right? So for vertex integrity, it is FPT in the simple case, which means also for this vertex cover. So the bound there is between like vertex integrity and deletion to stars. Then you have tree depth, then tree width, path width, whatever. And the rest basically remains the same. So like the tree-width dynamic programming basically remains the same. It's just easier.
And then I have one more question. What about something like planar graphs? You consider that?
I have not.
Okay.
It seems familiar. There may be results for that as well. I'm not now so sure. Right? You have bounded degeneracy, so that would fall in here as well somewhere.
Okay. Some more questions? If not, then let's thank the speaker.